Lecture 7, Law of Transformation. Now, consider a point P belongs to the intersection of the chart uxi and vyj, where xi and yj are labels, okay? Y and j is equal 1, 2, 3 in this case, okay? So, since the point P is invariant, which means it depends on the curvilinear coordinates, the Jacobian of the transformation between coordinates xi and yj for I is equal 1, 2, 3, I repeat, this is obtained. Now, I would like here to make a point. It's not only point P which is invariant. Any vector, covector, they are invariant in this case because it depends on the curvilinear coordinates. But the components, they do depend. Okay? That's very, very important for you. You see, that's to recall, okay, that set up, there's a chart, okay, this is a fantasy, okay. So this is a green one, is the chart which I can construct the chart uxi, and the purple one I can construct the chart vyj. You see, P belongs to the intersection, okay, of these two charts. And this is 0, this is a real number, which I build a point P that belongs to the manifold, M, in this case, M3. So, I would like to emphasize, to recall that I always say coordinates are functions. So, let's coordinate functions. That's the chart uxi. P here can be expressed, represented as this here, the coordinates x1p, x2p, and x3p. The same point P, which is invariant, belongs to this chart over here, is y1, y2, y3 at same point P. Now, coordinate transformation. Since coordinates are function, I can express each I here in terms of the coordinates y, in this case, y1, y2, and y3. Now, dxi, okay, from calculus, this is a partial derivative xi respect to yj, dyj. You see, now recall that dxy and dyj, this case, they are bases on the cotangent space T asterisk M. This equation will tell you, you see, how the basis dxy, that's I, is expressed in terms of the base dyj. Now, I would say the components is better, okay? So, because the vector, the cotangent space, they are invariant. So, this here is just clear that I can develop for I is equal 1, 2, 3, and I take the partial derivative. This leads to this matrix over here, 3 by 3 in this case. So this is called the Jacobian, okay? That's a capital J over here with the blue one. So there's a transformation between dy to dx. In this case, dyj, let's put in dxi. That's it. Now, on the other hand, okay, I could do the same as I did here, just saying that in this case, over here, over there, I put y over here, and this is the 3x over here. So then I always derive dyj. You see, dyj is partial for yj xi dxi. Again, from calculus, advanced calculus, which leads to, now this is the inverse of the Jacobian. You see, this is the Jacobian, okay? That is the inverse of the Jacobian. So, this case, the law of transformation for tangent vector. Now, this is a transformation for the cotangent basis. Now, the transformation for the tangent vectors could be transformation for any vector, okay? I just choose capital X, okay? It's xj partial xj. That belongs to the chart. Attention now, the same vector, that's important here. You see, the same vector, see? This here, okay? This is the same vector. I can also represent for different components, obviously, the x tilde k partial of yk. This belongs to the chart Vij, and these components belong to the chart Uxi. Now, we wish to relate this case xj to x tilde k. Now, recall from calculus, okay, that partial f respect to yk, it is a chain rule. You see, it's partial xi yk, partial xi of f, okay? I can erase f here and just write this relation over there. And also remember that this one is the capital J, is the Jacobian, okay? Now, since the same vector, you see, the same vector, I would like to emphasize this. The same vector can be written in different coordinates, you see? So this xy tilde, that's tilde k partial yk, this xj partial xj. So then I substitute, see, quite easy over here, then I can get all the relation here. So I will compare, you see, this one and this one. This leads to this relation over here, okay? It's quite simple, you see? I just compare and relate this with this xj. So xj is equal, you see, this part over here, okay? It's written over there, which is the Jacobian j. J is applied, in this case, by x tilde k. Again, could be any vector v, for instance, okay? So then, this is the inverse of the Jacobian, x tilde k is partial yk respect to xj, capital xj. These are the relationship between components, you see? So this the inverse of the Jacobian. So that's what I want just for you to say, and you see later, okay, how important is the law of transformation in the definition also of a tensor. You see that, see, that's important.